Good morning, everyone. Last time we started presenting the history of natural language processing, and we started presenting the first epoch, hand engineering features. So today I'm going to continue to go through the history until last year, and hopefully we can get into some future discussions. If not, we can wrap up NLP in the next lecture. And meanwhile, I'd like to encourage you to finalize your uh, project proposal, and we can have the proposal decided by this week or latest the next Tuesday. Okay, so after about 20 minutes into a lecture, I will pause for a few minutes so you can raise questions. And at any time, please enter your questions into the chat room. So we divide the NLP history into three major parts, and then we have this frontier research. And the last time we started with hand engineering models based on heuristics. And we motivated natural language is unique to human being. And from the DNA structures, the only difference from us, from our predecessor chimpanzee, is just the second pair of DNA. But however, with that difference, we are able to accumulate knowledges, and also based on the existing knowledge, and we do exploration to create novel ideas. And this is only unique to human. Other species, after they were born, they have to start learning from scratch. Of course, our DNA may already give us some priors. And if you listen to Professor Chomsky's lectures, and he will probably say, but this is an interesting hypothesis he made. He considered language is something like a lever. So when we are born, we have this language organ, this like prior. So we could pick up language very, very quickly, not because we are working extremely hard to pick up languages, but because we already have this intrinsic capability, already been pre-programmed. So you can probably tell virtually everyone, even just primary school graduate, they can speak language without any problems. But to do writing and to perfect your writing, of course, we need additional training. But just spoken language, it doesn't seem to take a lot of effort for us to be able to start to make conversations. So we had this example last time. We say, okay, suppose I went to Kyoto and I have seen a lot of different sceneries, and I want to convey what I have seen to my friends or family. And the only way I could do it, if this is about 1,000 years ago, even 200 years ago, there was no photography, right? I mean, unless I can just say I do a painting, I show my wife saying, wow, this is the beautiful scenery in Tokyo. Otherwise, I have to use speech. Today is much easier because we have images, we have videos, but 500 years ago, no, right? So language is only the mechanism for us to communicate what we have seen. So when we convey in language, the perception obtained by the audience may be different from our intent. So gradually, the language need to be further refined and refined. And if we look at this picture, we will talk about consciousness in week 9, but this is a preview. So by psychologists, we can divide our conscious state into 3. Unconsciousness, like our heartbeat is ongoing in unconsciousness state, pre-consciousness, and the consciousness. So today I'm not going to get into details, but you can think about how we position vision and the language. When we position vision on this two-dimensional space, on the left-hand side, I say micro. If we want to plot various applications on the graph, we can do that. But today we just look at the right-hand side macro. We compare vision and the languages. Where do you think vision should be placed? Should vision be in subconsciousness, pre-consciousness, or consciousness? Right? It's an interesting question. And I'm not going to give you the reasonings, but this is what most of people believe. Vision is unconscious in unconscious state, but it's also in preconsciousness state. And one example is suppose you are looking in a garden, right? And you are thinking about other things. But when a chimpanzee, that definitely wouldn't be chimpanzee, but an animal comes over, and you can see the animals, but then you realize suddenly you realize, okay, something going on. So our perception is ongoing, even we are not really interpreting the situations. So it's probably in the unconscious or subconscious state, and when we are alerted, and then we get into a conscious state. So conscious state, of course, language plays a big role, right? So this is the intuition behind where we place them. Uh, Definitely, we can do even much more. Let's say ethics. Where should we place ethics? And when we talk about robots today, they don't have ethics. A robot cannot commit sins, right? So, but if we want to put ethics into a robot, how can we approach the problem from uh, this kind of two-dimensional diagram? And those will be discussed in lecture 15. So come back to the past. So we started to say, okay, uh, before year 2003, the word representation is done by using this one-hot vector. And one-hot vector, the major shortcoming is you just cannot compute similarity. Okay, so that's given. So the remedy was people using this kind of handcraft graphs or structures to try to encode similarity. And in this particular work done by Princeton WordNet, uh, a lot of researchers encode this hierarchy of is-a relationship. So you look at picture at the bottom, dog, man, cat, they are animal. An animal is an organism, and so on and so forth, right? And later they consider, well, how can we depict has a relationship? A hospital has nurses and doctors, right? So again, that will require a lot of uh, hand engineering work. And you must know about this kind of tagging, right? Entity relationship tagging. A word is a verb, a noun, that's fine. But this word is a location or a name. Those just are heavily involving human involvement. And it's definitely not scalable. And the problem encounters not only similarity, cannot be precisely quantified. We could say man and a cat, they both belongs to mammal, but what is the similarity score? 0.3 or 0.7? So it's not really precise, and it's not context-based. And another problem is this polysemy problem, right? Four in Tokyo can be interpreted in different ways. So all these problems need to be addressed. So in summary, there are two major problems over the last 50 years, and all the researchers try to overcome. One is a synonymy. A word can have multiple words can share the same meaning. Car and the automobile, for example. So even more challenging will be like I say Mercedes-Benz and the Toyota. So do you think they are synonyms or not, right? The answer is tricky. You say, well, in the context of car, or in the context of luxury cars, they are not similar. But in the context of cars, they are similar. So synonym can also be context dependent, the strength of similarity. And polysemy is even a worse problem, right? Potato chips or computer chips. And even in one sentence, the word chip or the word fall can appear twice, and each one meaning different things. Let's say I go to a bank which is located in the bank of Charles River, right? The bank itself has two meanings. The first one is this commercial bank. The second one is the bank of a river. And chip could be the same thing, right? You say, can you chip in some money so we can go out to buy some potato chips, right? Um, so how to solve the problem? Initially, researchers using this kind of word called cursor matrix, and we described a very simple one last time. We need to decide, this is a two-dimensional matrix. We need to decide what are on the rows and what should be in the columns, and then what should be put in the cells. And the simple one is we just say, okay, we put all the documents on this column level and all words, maybe 300,000 words as this row, right? Then we say, okay, this particular document one, which words appeared? And then when a word appears, you can count how many times a word appears. So if once, against, just put one, and maybe this against in document 7, 3 times, we put 3 over there. So this is similar, sorry, this is a very simple co-occurrence matrix, but we can utilize the vector. Document 7 is depicted by a vector of words. We can simply use a vector to compute similarity, cosine distance function, or any kind of Euclidean distance function or other similar functions. But again, this is not really fine-grained. So definitely we are moving to be more and more fine-grained in the last few years. And with this word counting, so we already moving us from this not considering contextual information at all to consider contextual information within a document, right? So we are moving up. We like to be able to move to the right upper corner. So we took the first step. So the memory of merely occurrence, again, I mentioned is a relationship is there, but has a relationship is not encoded. So we need to solve the problem of synonymy and the polysemy. The BMW example has been given to you. And this was another example. Ellie plays piano in a play, right? The play, two plays, they mean different things. And a very famous problem in this particular dimension, two-dimensional matrix, is called market basket problem. You must have heard about this if you are majoring in computer science. So the problem is we go to market, we do shopping. What we put in the shopping carts, we put in the data structure. You say, I went to Trader Joe, I bought carrots, I bought milk, I bought potato. So initially, this market basket problem was trying to help the supermarket to decide their promotion. So if a lot of people they bought milk at the same time they will buy beer, so you can do some sort of promotion scheme. So one famous promotion scheme was during weekends, and a lot of men will be urged by their wives to go to supermarket to pick up diapers for the kids, and the men, I think us, right? Some of us would say, well, I like to watch sports, so I will buy beer and maybe potato chips at the same time. And the supermarket do this frequent item set mining. They say, wow, this association between diaper and the beer. That was really interesting in the beginning when they found out. So they say, okay, let me do a diaper sales, right? 30% off. Now you can imagine my wife would say, yeah, go for it, Edward. Diaper is off. It's on discount. Go to buy, get it. Then I look at the beer, and beer, they secretly raise the price by 30%, right? So at the end, the supermarket makes even more money. And I cannot say I don't go, right? So that's a scheme. Another one is if you have experience going to Costco. And so suppose I buy merchant 1 and 2, and they are at adjacent aisles. But next time I go there, I couldn't find the second item because second item was moved away. So this is another trick. They say, okay, most of people buy 1 and 2. So I like to shelf them as far away as possible. So therefore, you have to walk to look for the things. And then along the way, like as bad as I am, I will pick something original I don't need to buy. So many times I go home, my wife would say, why do you buy this? I didn't ask you to buy this. I say, well, it looks interesting. So this is another way using this kind of market basket kind of mechanism can address the promotion in the supermarket. But in general, this could be looked at as this kind of association rule prediction. Suppose a user has seen 3 photos, right? And we like to recommend the fourth photo for the user. And how should we do it? We say, okay, which photo has high associations with the previous 3? So you mine the data of all the usage pattern in the past. Then you say, okay, suppose a person look at A, B, and C. Now I want to add this D, and which D will give this probability, conditional probability, the largest value, right? So you look into the user's access patterns, other users' access pattern in the past, then come up with this very, very simple Bayesian interpretation. And there are some theory behind it. I don't need to cover today, but this is a very popular scheme for very simple ads matching or merchandise recommendation. And a small trick is this NABC need to be slightly large. If this NABC ABC pattern, it doesn't happen. It does happen, but doesn't happen very frequently. This is called the support is too low. So you cannot trust this prediction. But if you have ABC happen very frequently, so to predict D, and that makes a lot of sense. Okay, so how can we accomplish this kind of heuristic? What is the implementation? Surprisingly, it's very simple. So it's just a two-dimensional matrix. And on this two-dimensional matrix, like we mentioned about in this co-occurrence matrix, we need to decide what's on the axis and what is on the y. And you can do a lot of different things. You can say, okay, on this column, we have different images, we have different documents, news, ads. On these rows, we have every individual users, right? And the mission is when a user click on a particular object, we put on a cell 1, if not 0. And then the mission is to predict the missing value in this matrix, right? So let me see whether the next slide would, yes, the missing values. So we say for user number 1, should we recommend this first image or the 6th? And we don't know. So what can we do? We look at other users also access number 3, 4, and 5. So similar users, right? Suppose I consider this person, the second user is a similar user as myself. So the first object, no, I'm not going to recommend because the second user did not click on it. But he or she click on the 6th one. So I'm going to recommend that one to this user. And this is aggregation, right? Because I saw as a counting, if you have a lot of users, access 1, 2, 3, access 2, 3, and 4, at the same time, they will access number 6. Yes, you go forward to do the recommendation. So the flexibility, you can just put anything, virtually anything on S and anything on the Y, as long as they have sort of like correlations, right? And we can show even more examples later. But this is the cheapest, most rudimental collaborative filtering algorithm out there. Has been used by many companies. The major reason is computational not very intensive. And in year 2007, we made the algorithm run on parallel machines. So we parallelized the mechanism, and UC Berkeley adopted into its open source. So my question is, okay, then have we solved the problems? The answer is not really entirely, right? So the problem number 1 is we haven't encoded the strength of interest. Oftentimes I click an article, I look at the article, within a few seconds, I just go away. It's called a bounce because I say, well, I get trapped. So there are a lot of this kind of clickbait, right? You put some beautiful pictures on the page and to kind of seduce people to click. And people click on the page and they say, well, it's not what you said. And nowadays, a lot of news will put question mark behind a statement rather than saying, well, this is a summary of the news. They don't do that because you do a summary on the news. If you do a perfect job, no one will click. So they put some ambiguous statement. Well, what happens? Do you know? Then you get enticed to click. And the second challenge is the metrics tend to be quite sparse, right? So you consider all the merchants in Costco. So how many sales would you say one? Or how many cells would you say two or three? Most of the cells will be just a zero. And number three will be semantics, right? Just give you an example. Let's say, suppose I'm a new company and I haven't gotten a lot of advertisements from vendors. Suppose I only have BMW's advertisement, and I probably maybe I have Mercedes Benz or maybe two or three. But let's say you click on Mercedes Benz, and suppose I don't have Mercedes Benz advertisement, but I have BMW. I can say, oh, this is the luxury car. So I don't have to match you by your keyword. I can match you by your semantics, right? That will broaden my um, ads offerings. So that's one example of having a semantic layer can be very useful. And so this leads to the major breakthrough in early year 2000. This is done by Michael Jordan's group at Berkeley, and Andrew Ning was one of the authors. So the idea was, okay, we want to create a latent layer between words and the documents. Again, we don't have to put words and documents on two axes. You can put other things. But this example here is we like to be able to recommend users. User may do a search and we want to match with documents. So two examples on the top right. So suppose you do a search like iPhone crack, or you do a search like apple pie, right? iPhone crack doesn't have apple in there. And on the other hand, apple pie has apple in there, but this apple is not the IT apple. This is fruit apple. So it'll be good. So at the bottom, we see if it's good if we can build a latent layer, and the characters are very small, but the latent layer, you can see this. So we have four different categories here from IT, food, and history. And this is another one I couldn't read. So you say, okay, the first one, IT, iPhone crack belongs to IT, and apple pie actually should be food. Then when we do search, then because of this semantic layer, the accurate responses or the accurate results can be returned. Okay. And the second thing is we need to encode strength into the cells. We don't say just binary 0 or 1. We say, oh, you often access this particular document or this kind of document. So we bump up the numbers. And LDA, the algorithm, basically is extremely simple. We have this two-dimensional space, two-dimensional co-occurrence matrix. And this example here is a document and words. Again, you can have document users, right? And then we say we want to factorize this matrix into two sub-matrices. And the right-hand side matrix is the semantical matrix. So look at these words and topics, right? Basically, we can cluster words into topics. So this is good because suppose we cluster play this word under the topic sports, or we cluster play under the topic instrument, right? So different cluster, if the word play falls in under different topics, then you know the semantics of this particular word. And a word can appear on multiple topics. So this is not a strict clustering. The membership can be quite flexible. And the bottom layer is also important. This is basically doing classification, right? So you have news. One dimension would be news or documents. The other dimension will be the categories of your news, sports, politics. So you look at this algorithm, the output, very, very useful. And the complexity is about n squared. So let's look at an example. This is an example experiment run on 37K documents. And the documents consist of 26K words. And we set the latent layer number to be 1700 topics. Okay, the 1700 here is a tricky thing. You see how many documents you get. You cannot decide, right? You just scroll the document in, and how many words are there? It's a counting. These two numbers are given. These two parameters are given, but how many topics is very tricky. And if you can recall, like k-mean is an unsupervised clustering algorithm. You want to cluster your objects into k clusters without any labels. In those kind of situations, how to determine K is rather tricky. And here, we don't have time to get into how to decide K equal to 1700, but most of people just try and error. Suppose, okay, 1700, around 1700 are article topics coming from libraries, okay? So you get this 1700 clusters, and this is a list of example clusters we get, right? So when we talk about semantics or latent layer, each latent layer is represented by a set of words. Let's look into what's in there. So on the left-hand side, we have this character here, but you look at the other words in the same cluster, characters, okay, you say form, copy, and paper, or you say, okay, this is probably alphabetics, right? And the same character, when we go to the second column, oh, character, play, stage. Oh, this is a character in a movie, in a play. Okay, so in different cluster, the words meaning, depending on the context, is different. And the play, okay, we shift to another cluster. Play here, you see court, you see score. This could be play in the gym or maybe play tennis, right? And the core, we move to the next one, court, case, jury, evidence. Oh, this is related to law, to a trial, right? And then evidence move to the right-hand side again, correlate with experimental, scientists, and tests. This is a scientific experiment, and so on and so forth. So how do we utilize it? So every cluster has a ID. So when we go back to parse the documents, we assign every word with its ID number, right? So play here, the top one, we get 082, cluster from 82, and a play in the middle document 077, and finally 166. So this is fantastic. We get this through this very simple matrix factorization. We get semantics, right? Context-based semantics. So it seems like this polysemy problem got resolved. And this is really great. But there's one shortcoming which I would enumerate again is the play in article. Suppose the example I gave you, this I play piano in a play or whatever. So if you have two, the one word in the same document, but they can mean different things in different sentences. The granularity of the LDA is too coarse. But this is in the LDA, the disambiguation is only done in the document level, not done in the sentence level. Okay, so this is something definitely can be improved. And so issue summarize for polysemy is coarse grained. And therefore, those two examples I already talked about, and we need better mechanism. And for synonym, like for could be autumn, for could be drop, right? The Tokyo fall, and could be stock market fall, or the tree fall. And then in this situation, again, we cannot really quantify these different kind of synonyms in this LDA scheme. So in short, we need to have finer granularity. So now we get into the second epoch, and this is 5 years. This is 2013. Last time I motivated, the NLP community did not really get into deep learning until after they have seen the vision community was so successful. So in year 2013, a team of Berkeley people started to saying, well, can we encode contextual information in a finer grain? So this is a very important treaty by Harris, proposed in 1954. Uh, the treaty was very straightforward. The meaning of a word need to really look at your context, right? Or the word meaning depends on your neighbors, right? Or you can say your character depends on the friends you make, right? So that makes a lot of sense. But it takes how many years for us to be able to finally encode context into the sentence? Over 60 years. So we get started with the history. So now we're going to go to this word to vet. So word to vet is this happened after neural net started to be adopted by the NLP community. The idea was this one half vector was really bad. So suppose we can classify words into multiple classes. In this toy example, we have dog, cat, and bird. Then on the right-hand side, we have flower, tree, and apple. When we plot these words onto a simple two-dimensional space, because only on two-dimensional we can visualize, we hope similar words can be in the nearest neighbors. So hopefully the yellow color ones and green color ones and orange color ones, they are clustered, so they should be nearest neighbors in this embedding space. Okay, and that's a wish. And then the scientists at Google, this was discovered actually by luck, right? So they say, I want to put neural net and to just kind of interpret uh, document and whatsoever. And in these two papers, what they come up with two different schemes. The first one is called continuous bag of words. The second one is a skigram. The basic idea, if you look at the example at the bottom, is if I have a sentence, I have let's say 5 words, and I want to just I want to just get rid of the middle word. So the mission of the training becomes, can you train the machinery which can guess the missing word, right? So this is called continuous bag of word. So once you have guessed the middle word, then this sentence can continue to flow. The other one is called skigram. So suppose this is the word I'm given, say play. Can you come up with some nearest neighboring words, right? So this mechanism looks slightly harder. So we just focus on the left one. The right hand side will go through the similar computational processes. So the left one, the input will be one half vectors. And the output here, WT, will also be one half vectors. So this example here is our input is the cat blank on roof or on floor. And we want the desired output to be set because that's the ground truth, right? We just remove the middle word, and later we will come back when we talk about bird. This is kind of mask language model. So we get rid of the middle one, and then we try to guess it. And then this is just, we have made so many different sentences. We just continue to input into this mechanism. And the window size can be adjusted. Can be in that particular example, the window size is 4. We can have 10 or whatever, right? It's kind of flexible. And the input, again, one half vector looks really ugly. And the hidden layer, finally, this output layer, also one half vector. And in the middle, they have this hidden layer. And they only have one hidden layer. And for sure, it's accidental, right? People like to put hundreds of hidden layer, if not tens of hidden layer in the middle to perfect the result. But for some reason, by accident, whatever, they only put this one hidden layer. And the dimension in the beginning was 512. And later they increased to 1024. So what they discovered was, okay, so yeah, we get this neural net, right? You get this weighting matrix. By having many training data, eventually we train this weighting matrix of this WVN and WMV. So V is a dimension of one half vector. Suppose V is, let's say 300,000. And I just mentioned 512 or 1024, right? And then on the right-hand side, you like to be able to get this latent layer to produce your final prediction. And that would be another matrix. So this prediction will go through a softmax because at the end, we wouldn't actually get 0 and 1, right? We will get a list of probability, and then we use softmax to magnify the word with highest probability. Then we produce that word representation using one half vector. Okay, so hopefully the idea was not extremely complicated. So the advantage at the end we take is, oh, thank you for giving us this V multiply N matrix. And using this matrix, if this is the end of training, this matrix will give us one half vector mapped to embedding vector, this mapping matrix. And you look at this matrix here. And for this cat word is the second word. So if we multiply the matrix by our one-half vector, basically we are indexing into this weighting matrix to get the embedding out of it. So the embedding in this case for cat will be 2.4, 2.6, and so on and so forth to 1.8. The dimension is only 512 or 1024. Okay. For some reason, they didn't use these two numbers. I'm curious, if you are interested, you can type in your guess. What is the current numbers we are using in this word to vect? Just for fun, you type in the chat room. Between 1 and the value is between 1 and 1,000, right? Let's continue. In about 1 to 2 slides, the number will be revealed, just for fun. Okay, so we look at this. This is a way to get the V, and this is a way to get cat. This is the multiplication to get this on. Then eventually we can predict this set value, and this is again, this is a mechanism I just mentioned, and using this one-half vector to index your embedding or embedding. So the right-hand side shows the answer, right? So the original space is 300,000, and the dimension is actually very funny. It's 768. What is 768? It's 512 plus 1024 divided by 2. Why they came up with this number, I don't know, right? So they are just magics somewhere. So let me look at the chat to see. Yeah, okay, that's good numbers, 300 and 512. So 768, but it works really great. I bet those researchers have done some comparisons offline when they publish the paper. So turn out 768, but I just wondering why not 728 or 788. So I don't see signs here, right? I see empirical results here. Okay, now the fun thing starts. Based on this embedding, you can put, this dimension is, let's say 768. Still, the dimension is very high, but they are able to project this vector onto a two-dimensional space to visualize. And this example here is, once after projection, we can do this kind of interesting mathematics. King minus man plus woman equal to queen. This is interesting, right? The king is typically, actually that's true. The king is male, and minus gender plus another gender will become queen. And this is another example published in the paper. So this is a relationship between capital and a nation. And some folks using this relationship to perform all these different algebra. Like German is equal to Berlin minus Rome plus Italy. And you can do this kind of hotter minus hot equal to bigger minus big. Like this degree kind of situation can be quantified in this interesting way. So this is really solving the similarity problem in a very attractive manner, right? So this is give us a much better representation rather than just one-half vector as the input. And nowadays, virtually everyone doing this embedding first. Then they start the training. And slightly later, we will show the input from this one-half vector. They say the cats sit on the floor. So when we convert cat, we convert cat into embedding vector, the word to vect, but also we want to encode the position of this word. They say, oh, cat is the second word or third word. We need to be able to encode the position, and later the other side, when they get the information, they know where the words come from. So this is in the attention lecture, I would talk into details, right? So this is a representation transformation. So we again come back to look at this progress picture. Now we have this predictive model, not just word count. We are trying to predict the missing words, or we are predicting either the missing word in the middle or the surrounding neighboring words. The both mechanism will give us a better representation. And sort of like this is the beginning of considering context. But if we want to push ourselves, so this whole sequence is very logical, right? So at this point, you say, oh, okay, have we hit a home run? So everything is done, right? Not really. Still, we can do even better. So we kind of look at these uh, accomplishments from this word to back. For synonymy, good. It's pretty good. But for polysemy, it's still called scram. Because for every word in this word to vet, it only has one index, right? It's really easy to see. Once you get this vector on the right upper corner, suppose I have this word called play. You come into this matrix, there's only one representation for the play. So it's even worse than LDA. So wow, this is bad, right? So how do we solve the problem? Then we sort of like we make progress on synonyms, but we have this kind of digress, degradation on polysemy. So we go back to Harris to say, hey, Harris, please help us. And Harris told us the same thing. I told you for 60, 70 years, how come you guys just couldn't figure out a solution? So the scientists come back to redraw the solution on the board. They say, oh, we have done this word to vet. And word to vet, what's the input? One input is this one half vector. And thank you to give me this embedded vector. But hey, just put a context as your second argument. Okay, it's not very complex. Okay, this Harris already told us context. Okay, finally, in year about 2014, exactly 60 years after our grandparent told us to do the right thing, well, finally the community say, okay, let's put context in the computational model. So there are two major works. One is a sequence to sequence. The second one is attention. We heard about attention, right? So attention invented the word is coined by Chris Manning's team in Stanford, but only took off in year 2017 and 2018. And once the Google folks and implement this transformer model. So let's look at the design steps. So this is a problem we have seen so far. So let's go to this data-driven representation learning. So this far, still the community is doing a lot of traditional model preprocessing, similarity, dimension reduction, but data-driven. Data-driven sequence model details are in these two papers. So we look at this example. And this example shows how this sequence to sequence, or we call recurrent neural net, RNN model works. Okay. So why we call RNN, once we see the picture, we probably can figure out. So this is a translation problem. On the left-hand side, we have input tokens, three words. Then our sequence to sequence model eventually will generate four words, right? Suppose you thought about French and generate some English words and vice versa. The length could be different. And the sequence to sequence model in the middle take all the input and generate output. So let's look at even finer grain. The middle box, we open it up. We see an encoder and then we see a decoder. And let's focus on the interface between this encoder and the decoder. Okay. So this animation, we put word 1, 2, 3 into it. We generate context. We ship context to decoder. We generate four words. So if we want to be critical to this architecture, we would say the following, right? We say, okay, you have this input, one half vector. We convert this one half vector into word embedding. That's great. So that so far so good. Then we utilize this word embedding to start to conduct training. Step number one, we generate hidden state number one. Step number two, hidden state two. Then we get hidden state three. When we put hidden state in the middle and input to the decoder, then we generate our output, I'm a student. The key here, the key shortcoming here is we only input hidden state three into the decoder. Hidden three, one, and two, we did not utilize them. And this is a traditional called long distance dependency. We lost the long distance dependency. And this picture shows the mathematics, and it can clarify really well. So the bottom encoder, we take care of input. On the top, we do this output in the translation situation. So hidden layer generation on the top, the hidden layer T, when we generate it, it's a function depending on hidden layer T minus one. That's fine, that's straightforward. Depending on the previous output, Y T minus one. That's very logical. When you try to produce the translation, you already gotten the previous word. You get the previous word's content, hidden layer. You want to produce the next word, but the context given is only C. C is the last hidden layer produced by the encoder. Okay, so this C is the problem. And then we look at this inferencing eventually. Once we have gotten this HT, and we use HT and YT minus one and C to predict the next word. So again, here we only use the last hidden layer of the input. We have this long distance dependency problem. We lost a lot of information. So all the researchers are very logical, right? They say, oh, so I missed some long distance information. How can we solve the problem? So I'm going to encode long distance information in the model, right? So they say, okay, so we have this shortcoming, only get this final hidden state. And then we have this vanishing gradient because all these long distance ones, once they aggregate the heuristic, whatever, into the final hidden state, most of them are lost, right? So, okay, let's insert something in the middle. So this something is called short-term memory, right? This is LSTM, stands for long-term short-term memory. So some memory can be long-term and some memory will be short-term. So without getting into much details, let's say for translation, for nature language, what kind of states we would like to keep, right? So I say, okay, maybe we want to keep 3 different states. The first state is the subject. We want to know the subject type. If the subject is female, male, that would determine how can I deal with the verb, right? Do I want to put S behind it? And the second is time. Is the past, future, or present? That will impact the tense of my verb, right? So those are just 2 very simple examples. And of course, there are much more complex situations, which I will give a couple examples shortly. So the good thing about having this long-term, short-term memory is, suppose I want to generate a translation, and you don't depend on just the last hidden layer. You say, oh, I'm going to go back to your entire sentence to see what is your subject. If your subject is I, then I know I'm not going to give, the form of the verb will be the original form. If your subject is he or she, I need to put something behind the original verb. So then you keep on progressing this long-term, short-term memory. And every piece of data in a cell, so you can have multiple states. I enumerate 3 different states, but you can have even more. So the state, once they say, okay, yesterday, when you start to say yesterday, the state of the tense is modified. So we say we forget about the previous tense state. We change the state to maybe future or past, right? Yesterday is the past. They say, oh, yesterday I forgot to bring my book to the lecture, and tomorrow I will bring my book. So when you say yesterday, the tense was past, then when I look at will, right away in the gate, right, in the register or whatever, I'm going to modify the state into the future. So this is a very rudimental example, but hopefully you get a sense. The reason we're not going to get into details is no one is using this anymore. And the reason is the following. So for our RNN model, sequence to sequence, we already talked about the 2 major shortcomings. For LSTM with RNN, the major problem is cannot be parallelly trained, okay? And also it's very cumbersome. Suppose you could solve the problem well, but it just cannot be unrolled to take advantage of GPUs. And this is definitely a huge problem. So remember, I'm motivated when I at Google doing this kind of paleo algorithm research. I was ridiculed because the algorithm itself If it cannot be parallelized, nobody will use it, right? So here, the similar situation, yes, LSTM can solve the problem to a certain degree, encoding this uh, nearest neighbors context rather than far distance context, but it's really expensive to train. And so then came out this transformer using attention, and this really revolutionized the entire field. So we remaining of the lecture with our time, another 30 minutes. We cover transformer, GPT, and the BERT and their kind of fine-tuning kind of mechanisms. So I pause a little bit here to kind of see whether we have questions. So again, you can enter questions in the chat room. Okay. Okay, let's get into transformer. And I don't have the transformer picture here, but you know the movie Transformer, right? So this is an interesting article written about 3 years ago. And they say, well, drop your RNN and LSTM because they are not good. This is really straightforward sentence, right? Uh, in fact, and when I talk to my colleagues, I say, if you don't know anything about natural language processing before year 2018, you are not missing anything. So is that a happy statement or it's a sad statement? And to me, it was a happy statement because I did not know NLP whatsoever before 2018. And I picked up NLP just in the last 2, 3 years. And I'm doing okay because all those heuristic algorithms like LSTM, if you want me to do a lecture on LSTM today, I probably couldn't do it because I didn't dig into the code in greater details. But if I only need to learn transformer and the subsequent materials, and that's okay, that's tractable. Okay, so let's dive in. Attention model, written by a Google group. So the mechanism is very simple. This is a very famous picture, and we see this on the left-hand side. We have this encoder. On the right-hand side, we have this architecture of decoder, and this particular picture is specifically for the Google's purpose. They are looking into translation, right? So later we will talk about the language model. Traditional language model is given n characters, you want to generate n plus. And Google, the first sort of like model they came out with called mask language model. It's a different language model. So a language model is not really a common term. It's a specific term saying, okay, when I say language model, it means you are generating the next sentence based on previous words, right? So this can be more clear shortly. So for translation, we have input sentence. We eventually want to generate output. And here, I give you an example mentally. Input, maybe in French, and output in the beginning would be just a start character, right? Nothing, start. And then after we process the input, we get this array of attention, which I will depict shortly. And this array of attention will be inputted to the middle attention layer of the decoder, right? So this is the only place the decoder and encoder talk to each other, okay? Talk to each other means you do backward propagation back here, eventually in the training phase, you modify the parameters, and you do forward training in between here. So that's what's the motivation we came out with encoder and decoder. And the position encoding was critical because when you input a window of words into the encoder decoder, eventually you need to position which words is where, right? So encoding scheme Fourier transform is very straightforward. We just consider you'll be given, no research can be further done over there. And attention, simply speaking, involves in three data structures. One is a value vector. And the second thing is a key or index into the value vector. And the Q is the query. The query, you want to ask information from the value vector. So example, very simple example here is I have three values, 150, 175, and 45. Then I have no idea what they are, but I have a key vector. Key would say, oh, they are actually a weight, height, and age. So now if I do a query on weight, I will get 150. So here you can say, how can we get 150? So you can see quite clearly, I have to do a dot product between query and the key, right? When I do a dot product between query and key, I know, oh, you want to know weight. So weight, indeed, I cover that in my value vector. So that will be the first element. So go to the value vector, fetch the first element to return to the caller, to the query. Okay. So this should be very straightforward. And this is one simple attention block, right? So we have multiply Q and the K to then we scaled it. And why we want to scale it is again an empirical result. We don't want the value to be too large. And so the formula is we dot product Q and K to get the index. Then we get a mask. Then we get into the value, a vector multiplied by this value vector. Then we do a softmax, we get our results, right? Suppose we have multiple heads, and eventually we just aggregate, either concatenate in parallel, or we do a sum, a weighted sum at the end at the top level. So there could be two different ways to deal with multiple output. So we can talk about multiple heads in 10 slides. Okay, so this mechanism hopefully is quite straightforward, right? Just this formula, attention given Q, K, and V, we do a softmax. First of all, do a dot product between Q and K, and divided by a scaling factor because we don't want the number to be too large. And then we multiply with the value vector, and we get a result. And result again, the magnitude can be all over the places. We do a softmax, so we want to make sure the value eventually at the end will be between 0 and 1. Okay. And then, okay, then we just again, we look at the translation. Suppose we have French words 1, 2, and 3, and output will be English word 1 and 2. So input, output, VO, embedding, word to vect. And the position encoding keeps sequence positions, and each attention block takes 3 input, V, K, and Q. And since V is the vector of all hidden states of the input token, an output sees the entire input sequence. So we solve the long distance dependency problem by having this attention vector. So if the vector, let's say the size, the size of vector is 12, you can see 12 states, right? You can see either before or after, not necessarily just before. And you can see even bigger window, like in the birth situation, they divide the buffer of 512 into two buffers, 256 and 256. And one question I put forward you can think of is, why 512? If I process a document, let's say I want to do translation, you say 512, and I say, okay, maybe okay, right? But you say, well, if I do Q&A, I want to do Q&A on a particular scientific subject, and your input is a question. You say the question can only have 512 characters. I probably would say, good. I wouldn't have a sentence too long, a question too long. But you say the right hand side should be all the information possibly have the answer. 512, you must be kidding, right? 512 is just too small. So why 512? Think about it, and then we come back. So attention mechanism, the decision layer basically do a query, dot product to the memory layer and the values. So you do see all the values in the buffer. And through this attention mechanism, the right-hand side is an example. And you have this, the monkey ate the banana because it was too hungry. So this is it the banana or the monkey? Eventually by training, and you can see the weight, the attention, it, the thicker, the darker color means the attention probability. So we went through this softmax, right? The attention probability is higher for monkey, the monkey, but much lower for banana. So this attention eventually tell us it here, it is the monkey. Okay. So the next example is even more interesting. We say the animal didn't cross the street because it was too tired. So here you can say, oh, the attention pays to the animal. So the animal was too tired. But we're just changing the tired to wide. It was too wide on the right-hand side. And the attention is so smart looking at, say, oh, the animal cannot be too wide, right? The animal, the street can be too wide. So it's rather clever. It's really look at the context in a sentence level, and the context every words will be looking to, not just the last word. So pretty much we have this problem solved, I would say. If you can consider that there will be missing problem need to be addressed, and you can elevate the natural language processing to the next level. So here I'm going to give you a real world joke. And when I was at the UC, I writing my first paper, and we are classifying wild animal from domestic animal, something like that. So I had this misspelling of wild. I spell into wide. So my secretary just made a joke with me saying, "Oh, animal is wide. Oh, Edward, it must be uh, kidding." So indeed, I have this writing error typo. I did wide. So to me, then this NLP wouldn't work because I was saying the animal is very fat, like elephant or something. Okay, this is the last slide was an example. Sorry, I come back here. So see, this is how the attention works. Every word pays attention to all other words, not just itself, right? So and then we have multiple layers of attention. So like in the transformer layer, the encoder state, they have so many layers, I think maybe 60 some layers. And decoding state also has uh, maybe about 20 or 30 layers. So there's no limitation of how many layers you want to put there, depending on the task and the accuracy you like to accomplish. So the recent monster generated by OpenAI, do you know how many parameters are in there? So the more layers you have, of course, the more parameters you get, right? There are a few things determine your parameters. One is your window size. So the vertically, how many characters you want to see at the same time. The second thing is how many heads you want to have, right? The third thing is how many layers you want to stack your this attention block, right? So attention block, as illustrated in about 4 pictures ago, encoder has 2 or 3 and decoder has another 2 or 3. Okay, so the more complex your model, the better accuracy or the better kind of results you will be obtained. But the cost will be the number of parameters. The number of parameters decides the computational complexity and will demand a lot of computation powers or GPUs. In the case of GPT-3, maybe today we may not have time to get into GPT-3, but GPT-3 has 500 billion parameters and is reaching 1 trillion. I bet there are companies working on 1 trillion, even 5 trillion models. So we have, if you look at the scenario right now, the data we are having already been fully utilized, and people just trying to increase the depth of the attention layers to try to increase the number of neurons. Uh, a prediction was once we get into multiple trillion, the number of neurons in the model could be equivalent to the number of neurons in human brain. In GPT-2, the number of neurons in GPT-2 is equivalent to the number of neurons in a bee, okay? So you just keep on increasing but I don't know whether the effectiveness will be able to increase. So multi-head attention, uh, it's a mechanism to try to do a divide and conquer. Suppose I have this input window which is very, very long. I like to be able to chop into short segments, and then I can compute in parallel. And then eventually the higher level can give me this kind of cross attention. I wouldn't be able to lose the information I really need. And another motivation of this multi-head is you can really take advantage of parallel computation because the heads operate independently on the data, right? They share the same huge matrix. And here we look at query, key, and values. And conceptually, they are in three, or logically, they are in three different matrices. But the real implementation, they actually put into one physical matrix, put in the memory, and then you have this access to different regions of memory to deal with the situation. So remember, I mentioned this 512, right? Why 512? So here is a good time to maybe to think about why, because suppose I want to map from input to output, right? So input is 512, the output should be 512, and so on and so forth. So this 512 to 512 mapping, if I want to do attention to look at the entire window, either multi-head or eventually aggregate information together, we definitely need to have this 512 multiplied by 512 memory space. And if you increase to 1024 times 1024, it's doable. So after BERT, there was a model which my company is using that is 1024 called BART, B-A-R-T. Indeed, for many tasks, 1224 get much better results, right? Another example is I gave you this Q&A, but another example would be document summarization. And if we want to do news summarization, a piece of news is more than 512 characters, but typically can be under 1024. So if we do summarization just on 512, we have to chop a document into multiple segments, and that's not really good, right? So 1024, wonderful. But why not 1 million? And this is called Reformer. It was done by Google about 2 years ago, maybe 1 year ago. I don't remember the time precisely. But Reformer, you have this 1 million times 1 million window, or 1 million times 1 million matrix. It cannot be put in the physical memory. So then subsequently, there are a few work try to do this matrix reduction. And my team, we using this incomplete Cholesky factorization. And that's a very principal method in linear algebra. We reduce the dimension from n to square root of n. So that makes the matrix much smaller, can fit into the main memory without losing a lot of information. So the 512 window is not really limited by the logic of the algorithm. It's limited by computer resources. And because the memory size keep on getting increased, so nowadays 1024 is okay, but going beyond 1024, we have to conduct approximation. So let's recap this everything using example translation, right? So we have this decoder architecture on the encoder architecture on the left hand side, a decoder on the right hand side, and we going through the process. Let's look at final grain. The first word comes in. Sorry, this animation. Okay, I couldn't see the top bar. So the first word comes in. You start to generate the first word on the right hand side. And on the left-hand side, you just continue to generate the third one and the fourth one. And you can do this animation at home to really get a feel to see the details. And when I post PDF, sometimes animation doesn't come out, but I will precisely cite the sources of all these animations. Those are not created by me. Those are on the website. You can look at those individual tutorials. And this is a complexity of information path length. And for self-attention, the complexity per layer, n squared multiplied by d. So n squared is really the window size problem, like sequence length. And this is the bottleneck of the memory. And at the bottom, you see this is self-attention restricted. Restricted means, okay, you have to give me n. I'm not going to look into the entire n. I'm going to do a subsampling. I only want to look into R, right? So this can reduce the memory requirement. But how to reduce from N to R? Most of people just say, I'm not going to look into this entire sentence. I would entire 512 buffer. I'm going to just look into sub-sentences, like maybe 7 or 10 characters. And that will limit the power of this attention mechanism. And recent papers, some papers come up with this kind of multi-resolution. So you could have n by n. At the same time, you could do subsampling. And subsampling can be done in a sequential manner, or you can do it in a random manner, right? So there are a lot of, we can say, hacks behind it. And I typically, I don't care about those hacks, right? We care about principles. And hacks basically just saying, oh, we have this trunk, the tree trunk is there. I'm going to make it faster. I'm trying to make it slightly more accurate, right? So a lot of people publish papers say, oh, I get this 0.2% higher accuracy, but those are not really interesting because it could be data dependent improvement. But speed, yes, speed is critical, especially the inferencing speed. So BERT and GPT. So BERT and GPT, we talk about their language models are different. For GPT, it's a traditional language model, left to right. And for BERT, it's bidirectional. Why do they want to do bidirectional? We look at why, because a mass language model demands on that to be more efficient. So a key element here, but we keep on talking about small data learning in the first two lectures. And the breakthrough for this mask language model is you no longer need label training data because the data itself is your teacher, right? So you say computer vision, if you do compression, then you do decompression or encoding, decoding. Using this minimizing SNR as your objective function, you don't need supervision because data itself is your ground truth, right? You do compression, then you decompress back to as original as possible. That's your ground truth. Likewise, in NLP, I think I have to appreciate those Google folks come up with this mask language model. They say, okay, I'm going to predict missing words. You give me an article, I'm going to take away n% of words. So again, this n is the magic. And then you say, why not 5%? Why not 20%? Why not 50? If we take away too many words, of course, the guessing cannot be done well. And if we guess only just 2 or 3 words, it's not very powerful. So again, this is a magic of 15%. So you have this document, you take away 15% of words randomly, and you try to build this attention model to guess the missing words. So once you have done this for a very large corpus, because you don't need label, your document itself is your label, right? So this you are so-called self-supervised learning. So this big data is no longer you need human to labels, but the data itself is its own teacher. This is really fantastic revolution. I think this is even more revolution than than the attention model itself. Okay, so the Google did 2 things. One, the mask language model is different from the traditional LM language model. The second is they have this another task because they divide 412 character buffers into 2 sub buffers. And the first buffer is the first sentence, the second buffer is the next sentence. So every time they provide input into the BERT training, the transformer, they provide 2 sentences. And their optimization objectives, in addition to predicting the missing words accurately, they do a hack. They say, oh, can you predict whether the second sentence is the next sentence of the first. I found it's mysterious, but it actually improved the accuracy according to Google by 2%, right? It's kind of funny because if you look at poorly written articles, even you read a paper, you say, I'm going to swap some sentences. I move the first sentence or second sentence to be third or fourth, and I move some sentences up and down. Some poorly written papers, I wouldn't say poorly written, not so well written paper, not that logical, uh, kind of engaging papers, they still read pretty well. If you could go to news, I will argue the same thing, right? So for the language model, I'm coming back here. GPT is really doing generating the next word. The man, then next one will be the man went to. And for the BERT mass language model, we take away random words in the sentences, right? So in the top sentence, we have two sentences. In the top input, we have two sentences. The man went to the supermarket. He bought a gallon of milk. So this is an example. I say, uh, why you swapping a sentence uh, would be a wrong thing. I say, if I say he wants to buy a gallon of milk and the man went to the supermarket, semantically it's the same, right? Even more telling is the next one. The man went to a supermarket. Mary walks his dogs every day. So if you switch the two, it's not impossible people writing sentences like this, especially our diaries, right? So I have no idea why this is next. Here you say it's next is false, but who knows? It works. Okay, so to recap, the semi-supervised, they call semi-supervised actually is just self-supervised. And using self-supervised learning, we pre-train this, we call pre-train model, BERT. The BERT has all the parameters based on the optimization of its next and guessing the missing words. And we have this, the weight matrix, everything being trained. Then on the right-hand side, we start to say, oh, so what did you want to do actually? What is your target task? You want to do Q&A? You want to do this annotation, name entity annotation, or you want to do classification? Okay, now we want to collect uh, your domain data, your test data. Like here, I would like to do this spam or not spam classification. So give me your data set. Here I want you to provide labels, right? Because of pre-trained model, we have this initial prior. So this is a way we don't actually need to have a lot of label data. So the label data of maybe a few thousand will be sufficient. Otherwise, in the past, we need tons of data because we need to train the bottom layers, right? The image in the image domain, we have given this example of edges and contour as a bottom layer, and we can do transfer learning. Here, the same thing. The BERT pre-trained model already trained all the base layers. Then here we just need to do fine tuning based on our supervised task on the top. So let's look at fine tuning. The first one, just say we enumerate a few very kind of dominant application, recommendation, information recommendation, summary, document classification, Q&A, name entity recognition, sentiment analysis, and so on and so forth. And this is one example of fine tuning. We want to generate class labels of a document, right? So input will be just the documents itself, and then we input into the BERT, and then we provide labels on the top to do fine tuning. So what fine tuning would do would be on the top of BERT, we may create a shallow neural nets. So fine tuning is based on the bottom layers. We do fine tuning on the top layers of our so-called adaptive or fine tuning layers of weights. And eventually we train our model for the target task. Likewise, we can do QA. QA, left-hand side is a question. Right-hand side is your paragraph. We ask a question to say, what is the weather tomorrow? And then the output will be the start position of the answer, end position of the answer, and the span. The span will be 7 characters, whatever. Then you look into, at the end, actually, if you have start and end, you don't need span, but for some reason they put span here. You extract the answers out of the paragraph. And this is quite limited because the paragraph here is only very short, about 216 characters. And this is uh, sentence tagging. We want to tag place and person on the sentence. Again, we go through this fine-tuning process. So given the sentence, eventually John lives in New York, we know John is a person, New York, those two are locations. So there are many successful stories. And this figure shows using BERT pre-training model, the results on many tasks, and performs much superior results compared with you have this one vertical. You do training by using traditional supervised learning method, right? So definitely you see revolutionary results. So nowadays people start with pre-trained model without having any questions asked. So GPT-2 using this traditional language model, they are also perform very remarkably well. I would say both GPT and the BERT, the concept is equivalent, and just their language models are different, and the results are very similar. Both are very powerful. And congratulations to the whole community. Finally, we virtually get all the problems we enumerated in the beginning addressed. Okay, so next time we'll come back to see slightly more fine-grained details, but hopefully, so far this lecture, we provide this history in 1.5 lectures of NLP, and we can comfortably move forward using the pre-training model. Of course, the next question will be, wow, there are so many pre-trained models, which one I should use, right? And there I have this multi-model situation, multilingual situation, and I'm in the medicine, so your BERT pre-training model may not be applicable. Let's talk about them in the next lecture. Okay, thank you so much. Questions?